Okay. Um. Welcome. Um. I. I know that beginnings are hard. And when we're starting to learn a new topic, it can be, challenging, frustrating. But we need to be patient with ourselves. Today, I'm gonna start by just practicing, a lot of different problems. Starting with one of your homework problems, and then I'm going to introduce you to some the optics of the eye, the optics of microscope, optics of a telescope, those sorts of things. And that's the goal for today. Would someone be willing to open our class with prayer today? Sure. I'll do it. Our dear kind Heavenly Father, we're grateful for the opportunity we have to learn and to grow, to make decisions and find our way through this mortal existence. We are grateful for the opportunity to help one another as we do so. We ask a special blessing upon these young people that they might be able to meet the many challenges that are on their path, that they might be buoyed up by thy Spirit, and that they might be kept safe while they are taking care of all the many responsibilities that they have. We ask a blessing upon those who are not able to be here because of circumstances. We ask a blessing upon those who are suffering from illness. And this we pray in the name of Jesus Christ. Amen.
Amen.
Okay. Let's start by taking attendance.
Thank you.
If I could get some help handing out handout. Thank you. Anyone else help her? Good. Help her over here. You look like it. Okay. What they're handing out is the published tutorial homework for this week's tutorials. Now, we're not going to collect this. You don't even have to use it if you don't want to. But the homework on Match, on the computer, asks you to predict the location of the image relative to, is it over here? Is it over there? You've got different labeled positions. And you really need to do a ray diagram to find where that position is. You can't just be guessing. And so rather than do your ray diagram on a computer screen, I thought it might be good to use a ruler. And so that's why I'm giving you a handout here in violation of all copyright laws. Okay. Okay. Last call. Good. Does anyone not have a handout? Raise your hand. Thank you. Okay, let's review really quick what we know about curvature. We know that when I have a wavefront that's diverging or spreading out, that's negative curvature. And the curvature is just the one over the radius of the circle that this curve is part of. And so the bigger the radius, you know, if you got a huge radius, if I just look at a slice of that circle, it doesn't look very curved. But if I have a very small radius, a slice of that circle is going to be very curved. Now, if the wavefront is coming together, it's going to be a positive number, 1 over the radius. And we find that if we can just keep track of when things are spreading out and when they're converging, we'll never have problems with minus signs, okay? All of the conventions and the tables and everything like that, we won't need. Also, when we deal with these problems that have more than one lens, you know, multiple lenses, if we can find the curvature after the last lens, if it's positive, you've got yourself a real image. If it's negative, you got yourself a virtual image. That's, you know, even in complicated problems where there's lots of lenses, you just got to look at what comes out of that last lens. And is it curvature that's coming together towards a single point that's going to be a real image that I could project on a piece of paper? Or is it spreading out as if it came from behind the wall and it's going to be a virtual image? Now, we had this formula, and the curvature before the lens plus the power of the lens is going to give me the curvature after the lens, okay? But this formula is only good with a lens. And this is right before the lens, not over here. It's right before the lens. And this is right after the lens, okay? Not over here. It's right as it leaves the lens. It's just like when we were conserving momentum in Physics 105. If you use that conservation of momentum, P initial equals P final, the initial meant right before the collision. The final meant right after the collision. You couldn't wait until that car skidded across the pavement and ended up in someone's rose bush. Okay? Now, in this case, it's negative because it's spreading out before it hits the lens. All converging lenses are positive power. Okay? And you can recognize a converging lens because the center of the lens is always going to be fatter than the tips of the, here in the middle is always going to be fatter than the ends. And that's going to slow down the middle of this wavefront more than the edges. And that's what causes the curvature to become positive on the other side. Okay, is the slowing down of light in the glass or whatever material it happens to be. So this would be a positive lens, and it's positive enough to change the curvature to positive. I'm going to try to always put negative quantities in red, positive quantities in blue, just to visually give you a heads up there. Now, we found the power of these lenses by starting out with nothing. If we bring in a plane wave, which is just some source far, far away, I mean, let's face it, if you look out the window and you're looking at the mountains, if you're looking at Timpanogos, those rays that are coming towards your eyes, they're all coming parallel to each other because they all started at the mountain and they all fit right inside that tiny little hole in your eyeball, okay? And so you've got rays that are coming parallel, and that's a plane wave, and that has zero curvature, okay? And if I give it zero and I get something else coming out, and we know what that something else is, all of these rays focus down to the focal point. And so the curvature right here is gonna be 1 over the focal length. 1 over the focal length. And that's how we find the power of a positive lens. For a negative lens, it's the same thing. You give it 0 and see what comes out. Well, you remember, for a negative lens, the rays spread out as if they were coming from back here. And so the focal length here is negative. And so, or you can put the minus sign out in front and make this absolute value of the focal length. So again, anything that's converging or causing convergence, positive. Anything that's diverging, spreading out, or causing divergence, negative. Okay? Now, these wavefronts evolve. Okay? Right here, if I wait until this wave goes half a meter, well, the curvature is going to be 1 over that half. And you know 1 over half is 2, so that'd be 2 diopters. If I wait until it gets 1 meter away, well, I know that 1 over 1, I can do that in my head. Okay, that's going to be 1 diopter. And it's negative because it's spreading out, diverging. Now, if I wait until it gets 2 meters away, well, that's going to be 1 over 2, the curvature, or 0.5. And you see how these curvatures are getting smaller. That should speak to your soul. They're not as curved. They're more like straight lines. And so if I go 3 meters out, now it's only 0.33 diopters, and it's negative again because it's spreading out. Now, you had this problem in your homework, the last homework assignment, and it really threw some of you for a loop. You're told that right as it left this converging lens, this convex lens, sometimes we call it, I like to call it the converging lens, it had a curvature of +5 diopters, okay? And you had to answer, well, what's the curvature after it travels 8 centimeters? What's the curvature after it travels 12 centimeters? And a lot of you had difficulty with it because you were trying to plug it in to this formula. You know, and this formula only works from one side of a lens to the other side of the lens, okay? We're already past that. It's already gone through the lens, okay? There's no P in this problem, except in the spelling, okay? Now, what we want to know is, you know, where's it all going to come together? Well, curvature is 1 over the radius. So that means radius is 1 over the curvature. 1 over 5 is 0.2. 0.2 meters is 20 centimeters. So with this kind of curvature, this thing is all going to come down to a point in 20 centimeters. Well, what if I let it move to the right 12 centimeters? What's the curvature of this one here? Well, I don't want to use the 12 centimeters. I want to use the radius of this circle, okay? And that would be 8 centimeters. And so if I want the curvature there, I would say the curvature is going to be 1 over 8 centimeters, which is 0.08 meters. And that's going to give me a curvature of positive 12.5 diopters. Okay, a diopter is just an inverse meter. Okay, is that making sense? Now, when I get here, the curvature is infinite. Now, we're not really sure how to enter infinite into max. And so we said, you know, if your answer is infinite, put a 0 so we can give you points. Okay, but I almost wish that we had said, if it's infinite, put 6 billion, you know, because it's big. It's not 0. It's big. Now, once it all meets here, it spreads back out. Okay, and this is that's what I see there is a real image, because now all the light rays are gonna spread out from there, and when they come into my eyeball, I see an image there. And if I were to put a piece of paper there, I could project that image onto that piece of paper. That's how I recognize a real image. But ultimately, when these problems get complicated and you're wondering, real, virtual, just look at the last lens and what comes out of it. If what comes out of it is positive, you're heading towards a real image. If what comes out of the last lens is negative, you're going to end up with a virtual image. See if your neighbor is following along here. Okay. Now, suppose I go another 20 centimeters and you each had a different number. You know, some of you had a total of 64 centimeters. Well, if your total from the lens was 64 centimeters, you were 44 centimeters from the place where it all came together. But let's say I only go 20 centimeters. Well, now my curvature there is going to be 1 over 0.2 or 5, but it's a negative 5. Oh, and what did Greg do? Greg made a mistake. That should be red because Greg promised it would be. I lied. Okay, live with it. Okay, that should be red, but it's negative because it's spreading out. Okay, sometimes you can learn from old people's mistakes. And then remember, if I make 3 mistakes, your tuition is free. Okay, this is a problem straight out of this week's homework that's due Friday. Okay, you've got 2 lenses. One that has a focal length of 40 centimeters and one that has a focal length of 10 centimeters. So quickly, calculate what the power of those 2 lenses are and tell your neighbor. What's the power of those 2 lenses?
But power is. That makes sense. Well, yeah, you're playing going to. Like, let's say
Okay. The power is going to be a positive 1 over the focal length, and that's going to be a positive 1 over 0.4 meters, and that's going to be 2.5 diopters. Over here, the power is going to be positive 1 over the focal length. That's going to be positive 1 over 0.1 meter, and that's going to be 10 diopters. Again, positive. Now, notice that the lens that has the smaller focal length is the one that has the bigger power. And also notice that I've drawn it fatter, okay? That second lens has a bigger effect on the wave. The power is what tells you, how influential is it going to be on the wave as it goes through there. And in order to really change the curvature of the wave, it's got to be fat to slow down the middle of the wavefront a lot more than the edges. Does that make sense? The smaller the focal length, the fatter the lens is going to appear. Now, so the first thing we do when we have these multiple lenses is just to treat them one at a time. And so we start with this first lens and we say, whatever curvature I give it, plus the power is going to be the curvature that I end up with. But this curvature is right there, before the lens. And this curvature is right here, after the lens. Now, the curvature, when it gets right here, is -2 diopters. Tell your neighbor how I got that. Where did that -2 come from? Did I pull it out of my ear? Where did I get the -2 from? Okay. All of the light, let's say I'm looking at the light that came from the tip of this arrow. All of the light spreads out with a radius of, well, 50 centimeters, we can say different ways. We can also say that 1/2 meter, okay? And the curvature is going to be 1/2. Well, 1/2 is 2. And the minus sign is just because it's spreading out. Does everyone see where I got the -2? No. So let's try. So the K is going to be, it's going to be negative because it's spreading out, and it's going to be 1/0.5 meters. If you plug in 0.5 meters and hit 1/, on your calculator, you get 2. Okay, is that good?
It's negative because it's spreading out.
It's spreading out. Yeah, as it moves from where I want to know what it looks like right before it gets here. And when it gets here, it's got negative curvature, the rays spreading out. Okay. And then we've got this converging lens with a power that we said was 2.5. And so because the power of the lens is bigger than the negativity of the wave that came to it, I end up with a converging curvature on the other side. Okay. Now, that curvature is right here. And so the question is, and notice this is not drawn to scale here. That's 1/2 meter and that's 2 meters and change. What's gonna happen to this wavefront of 0.5 diopters? Where is it going to come together? How far does it have to travel before it comes to a point? Tell your neighbor, how far does it have to travel before it comes to a point? Okay. If curvature is 1/r, then r is going to be 1 curvature, and that's going to be 1 we said the curvature was 0.5 diopters, and so 1/0.5, we just talked about that, that's 2. And so, this thing is gonna come together in 2 meters, which is 20 centimeters from the other lens. Are there questions on that, where I got that 2 meters from? Yes, Miriam.
If I wanted it from the distance of the object, would I have to add 50
Oh,
centimeters?
hold on here. What's that?
If I wanted the distance from the object, would I have to add 50 centimeters to 25?
Yeah, if you wanted it from the object, it would be 2, but we always do it from the lens. Cause that's where we got the curvature, was right on the right side of the lens. And so that's why we use the got the 2 meters there. Now, it turns out that that image, well, first of all, it's a real image because it was formed by a converging, oh, I just gave the answer. Is that real or virtual? Oh, good, because Greg just said it was. I'm slow. Anyway, it's a real image and it's 12 millimeters tall. Now, Greg, where did you get that 12 millimeters? That just pull right out of your head? That's a skill you need to have in your toolbox. That's a valuable skill. And that is, if this image is 4 times further away from the lens than the object, it's going to be 4 times bigger by similar triangles. Okay, well, I've got 2 meters on this side. I've only got half a meter on this side. I've got 4 times the distance on this side. So it's got to be 4 times bigger. See if your neighbor understands why that is.
Oh, yeah.
Okay. The key to understanding this is the ray that goes through the center of the lens and just goes straight. Because it goes straight, this angle is going to equal that angle, and that means that these 2 triangles are similar to each other. And that means that if this is 4x and this is only x, if this is h, this is going to be 4h. Oh, and that's a club that does farming. You didn't know that because you're city folk. Okay. So you see why it's got to be 4 times the height? Moving right along, let's now treat this as the object of this lens and find out where its image is using our standard equation. Now, I put this in red because once the light gets here, it focuses down to this real image, it spreads out again. And so once it gets to this lens, right on the left of that lens, it's going to be negative. And how negative is it going to be? Well, the radius is 0.2 meters, and 0.2 meters of a radius is going to give me a curvature of 5 diopters. 1 over 0.2, plug 0.2 in your calculator and hit 1 over, you're going to get 5. And it's negative because this is spreading out as it leaves the real image. Okay. Now, we said that the power of this fat lens was 10 diopters. And so that's going to change a negative 5 diopters into a positive 5 diopters. But that's going to give me an image that is on the same distance on the other side. Because I have negative 5 here and positive 5 here. They both correspond to a radius of 20 centimeters. And you'll notice that I made this the same height because they're the same distance from the lens. So far, so good? Now, big question. Is that image real or virtual? In other words, if I were to put a piece of paper here, would I see projected on that piece of paper an arrow? Would I actually be able to project that on a piece of paper? Talk to your neighbor. Which is it, real or virtual? Okay, I hope you said it was real, okay? Now, I suspect that some of you are feeling a little betrayed right now. Because last day that I taught, I was telling you that a real image is always going to be inverted from the object. Well, that's when I'm dealing with one single lens or mirror, okay? But when I've got multiple lenses or mirrors, I always just look at the curvature coming out of the last lens. If that's positive, it's a real image. If it's negative, that's a virtual image. Now, the other way to see it is that this is not the image of that. This is the image of this. And this is the image of that. Okay? And so this is inverted relative to the object that it's the image of. And this is inverted relative to the object that it's the image of. This, if you will have it, is an image of an image. Whoa. It's an image squared. Okay. You take -1 and square it, what do you get? Why would you? Okay. Now, noch einmal, that's German for let's do this again. Unama. Okay, this is right out of the textbook. We have a 2 centimeter ladybug, 20 centimeters in front of this lens with a power of 10 diopters. And then we put a second lens. This one is a negative lens, a diverging lens of 30, -30. Now, the first thing we want to do, well, I'm just going to replace that bug with an arrow because I wasn't sure how to draw a bigger bug. So just let's treat it as an arrow. We want to look at what happens right here. And this initial curvature is the curvature right there. Now, we know that if it all starts right here, the radius when it gets here is going to be 20 centimeters or 0.5, I'm sorry, 0.2 meters. The radius would be 0.2 meters. The curvature is going to be 1/0.2, and that's going to be 5, and it's negative because it's spreading out. Now, we've been here before. This looks a whole lot like what we saw with the last problem. And so I expect that my image from this first lens is going to be 20 centimeters to the right of this lens. Well, 20 centimeters to the right of that lens is going to be over here. Okay. Now, that never gets there. Okay. That's the way, that's what it would appear if this lens were not there. If it were not there. Okay. But it is. So what happens? Well, this this curvature of +5 here is going to get, it's gonna get bigger and bigger and bigger and bigger. As this comes together, it wants to come together at a point right there. But it doesn't. And so, what's the curvature when it gets right here? Well, remember these waves are concave. And their center is right there. So when this wave gets there, it has a radius of 5 centimeters. And, if this were the only lens, would this be a real image or a virtual image? Shout it out.
Real.
Real, yeah, good, okay. Now, because this curvature has a radius of 0.5, that's gonna be 20 diopters. That's a really tight curve. It's got a radius of only 5 centimeters. Everyone see where I got the +20? And then this -30 changes my my curvature to a negative curvature. Now I've got -10. So that curvature, the final, is right here. And the question is, what's that gonna look like? Well, it's gonna be away from the spreading out from a radius back here. If it's spreading out, it's gotta have the center of the circle's gotta be back here. 10 diopters, that's going to be how many centimeters of a radius? We've seen this before. Yeah, it's gonna be 10 centimeters, okay? And so it's gonna be 10 centimeters behind this lens. Now, if this is 2 centimeters and 5 centimeters to the right, then this is going to be 4 centimeters because it's twice as far away from this lens.
Could you quickly explain how you got 20?
How I got 20,
Yes, about 20.
the,
20 diopter. Yeah.
For the K1.
oh, this 20 here. Okay, yeah. So when it came out of the first lens, it had +5 diopters. And that told me that the center of curvature was over here at 20 centimeters away. Because 1/5 is 0.2 meters, okay? Now, that's gonna progress. It's gotta move 15 centimeters to get to the next lens. And when it gets over there, if it's moved 15 centimeters, that means the radius of this curve is just gonna be 5 centimeters or 0.05 meters. And if I plug in 0.05 and hit 1/, I get 20. Does that make sense? Okay. So now the question is, where's my advancer? You people have young eyes. Where did it go? There it is, my finger. Real or virtual? Oh, I found it. Real or virtual?
No, I was just gonna. We get to 20 centimeters, why do we add the 5 to the other side?
Oh, because the 20 centimeters is from this lens. And it's 15 centimeters over here, but I haven't gotten to the center of my circle yet. The center of my circle is 20 centimeters from there. So I've got to go 5 centimeters past. Is that- Oh, why is that on top? Instead of on the bottom? The let's see, I can answer this. Oh, yeah. If I look at the. Let's look at the ray that comes from this lens. And let's see. If I look at the ray that comes from this lens through there. And then look at the ray that comes through here and there. Oh man, this is not something that I can do without a ruler. Let me get back to you. Okay, let me get back to you. Okay, so that's going to be virtual because the last lens gave me a curvature that was negative. Okay. Last. Okay. Yes.
Why is the arrow on the left? Why is the new arrow, the 4 centimeter tall one on the left? Is it that?
Oh, because this is negative curvature, meaning it's spreading out this way. And the center of its circle is going to be to the left of the when the rays are spreading out, they're going this way. And so when I'm looking for where they're coming from, it's got to be to the left by 10 centimeters.
It's virtual, so I think it's slightly on the left. What does that actually look like?
What does that look like if I were looking through that second lens? I'd have to be looking through it. I would see what appeared to be an arrow there. But if I put a piece of paper back there, it would not project onto the piece of paper. It's just where the light is appearing to come from, because after it goes through that last lens, it's spreading out. It's not coming to a point, but it is appearing to come from a point that it's not really coming. Okay.
So I understand by the map why it's virtual. What would the wavefronts look like on that second lens?
What is the,
Like those wavefronts that you draw sometimes?
when it comes out of the second, when it comes out of that second lens, it's got a negative curvature, and that means that it's coming out like that. But it's already negative 10 diopter here, and so it's going to it's going to get down to negative infinity somewhere back here. If I look at the rays, which is up, we're always perpendicular to these wavefronts, they're going to be spreading out as if they came from a point back here.
Okay.
Okay. Okay. What if we throw a mirror in there? Okay, let's throw in a mirror. Just to make this more fun. If I have a source far, far away from my first lens, that is going to give me, rays coming in that are parallel, which that's what we call plane wave or curvature of zero. They're not curving. And so when I look at that very first lens, I'm giving it zero. And its power is given as -4 diopters. And that's what I end up with. If you start with 0 and you give it -4, you got -4. Now, what's the radius of curvature for, if the curvature is -4, what's my radius going to be? Well, 1/4, which is 1/4 or 25 centimeters. And so that means the image is going to appear like it's coming from this point back here, another 25 centimeters behind that first lens. Okay. So now the curvature here is going to be negative because again, it's spreading out. But now that light appears to be coming from here. Okay. It was already spread here by 4. So now this is now going to be -2. By the time it gets here, the center of it is 1/2 meter. And if I take 1/2 and do 1/4 that, I get 2. And it's negative because it's spreading out. Okay. And then I take this positive power of the curved lens, which is +5, and that gives me a +3. Now with a mirror, you got to fold everything back. And so now, plus still means what it used to mean, namely converging. But when it hits a mirror, it changes direction. It's no longer going to the right, it's going to the left. And if it's going to the left, it's going to hit that lens again. Whoa, twice the fun. We get to play twice, okay? Now, the question is, what does that wave look like when it gets to the lens again? Well, if it has a curvature of +3, that means it's heading to a point that's 1/3 meter away from that mirror. Well, looky here, 1/3 meter is a little bit further than 1/4 of a meter. How much more? Well, let's do the math. 1/4, no, let's do 1/3 minus 1/4. Well, I got to put those over a common denominator. That's going to be 4/12 minus 3/12. And that's going to be 1/12 meter. Okay, so it's going to appear like it is coming from an image that is 1/12 meter to the left of that negative lens. Okay, so now when I put in the curvature, when it gets to that wave, well, it's coming down with a radius of just 1/12 of a meter. 1/1/12 is 12. And so it hits that lens again with a curvature of +12. It's got a power of -4. That's trying to spread it, but it's not powerful enough to make it negative. It's still going to be positive. And so what I'm going to end up with is an image that is 1/8 of a meter away from that last lens. If the the curvature is 8 plus 8. It's going to be 1/8 of a meter away where it all comes together. And the question is that real or virtual? Yeah, it came out of the last lens with positive curvature. That's a real image. Okay, talk to your neighbor. Do a buddy check. Make sure everyone's still with us. Is it Scott? Okay, can I call you Scott? What, you had a question? You're just waving your arms? Okay. So let's move on to talk about some optical instruments. It turns out that with a curved mirror, we talked about the light coming in parallel would be focused down to a focal point. Well, that isn't really true for a spherical curved mirror, a mirror that's been made out of part of a sphere. For a spherical curved mirror, you get the rays kind of coming to the same general area, but not exactly the same point. A parabolic mirror, they would all come exactly to the same point. But parabolic mirrors are very hard to make. That's challenging. And so what we find is that if we have a small spherical mirror, then the lens maker equation gives us good answers. And the ray diagrams give us a good answers. They give us the same answers. But if we have a large spherical mirror, neither the lens maker equation nor the ray diagrams give us a good answer. And so the question is, what do I mean by a small spherical mirror versus a large spherical mirror? Well, if I look at a parabolic mirror that's really hard to make, and I look at a spherical mirror that's easy to make, but wrong, well, I notice that these two are pretty much the same as long as I keep right in this region here. If I use that part of the mirror, I'm going to get good results. And what that means is that I want the diameter of the mirror, that's from here to here, to be much, much smaller than the radius of the mirror. I want it to be a small slice of the mirror. Okay? Does that make sense? Okay. Okay. Now, let's talk about chromatic aberration. What does that mean? Well, chromatic means color. Aberration means it's just messed up. Okay. Now, if I look at all the red light that comes from this object, and notice that it gets focused right here, where will the blue light that comes from that object be focused? Knowing what we know from last lecture on optics, is it going to be in the same place, closer to the lens, further from the lens? Let's use our clicker again. Okay, last call. Good, the answer is B. Remember, BBB, blue bends better. Okay, so when the blue light gets there, it's gonna slow down more than the red light did, which means it's going to bend towards the normal more than the red light did. And so it's going to end up closer to the lens. Now, that causes problems when you're taking pictures, unless you're doing black and white. And so what you end up with is pictures that have colors kind of blurred. And so you got green on one side and blue on another side. And then you can correct that with different techniques. It turns out that that's what you pay for in a more expensive camera and a more expensive set of binoculars. If you buy, I've done this, you know, I have bought cheap binoculars and I have bought Swarovskis. Okay, the Swarovskis only cost 20 times more, you know, just a simple 20 times more, but they are 100 times better. And if you look at what they put in that Swarovski scope, there are just all these different lenses that are meant to correct these different issues with color and the chromatic, the spherical aberration, the chromatic aberration. And that will not be on the exam. I just want you to appreciate that they do a whole lot of fancy optics to get the nice, clean, sharp picture of the elk. Okay. Let's talk about the eyeball because you've got some homework problems that deal with the eyeball. It turns out that the eyeball is very, very similar to a camera in that it's got an iris that essentially controls how much light gets in. In a bright room, your iris kind of closes up into a nice small hole. And when you're in the dark, it opens up. Most of the bending, the refracting, happens in this cornea. And it's got a power of 40 in a typical eyeball. And then you've got this lens. And the important thing about the lens is that it's variable. These muscles can stretch that lens or relax that lens to change its power from 20 to 24. It's the fine tuning. The cornea does most of the heavy lifting of focusing down the light to your retina back here so that it can send the image to the brain. But it's this 20 to 24 that I can use to focus things so that they get right here where they're supposed to be in sharp focus. Okay. Now, it turns out that as you get old, take it from me, these muscles don't work the way they used to. And so suddenly you don't have that 20 to 24 range that you used to have. And that's why I'm wearing these reader glasses here. Now, other people are just born with eyeballs that either have a lens that's not strong enough or too strong, or an eyeball that's not the right length for their lens. And so that's when we get difficulties like nearsightedness and farsightedness. We need to define some things. A near point is the closest distance at which the eye can focus clearly. For a young, healthy human with good eyes, that should be 25 centimeters or about 1/4 of a meter. Okay. Now I put my hand right there and it's all fuzzy if I'm not looking through my glasses. Put my glasses on and now it's clear as can be. I can see my fingerprints. Okay. Now, normal is about 25 centimeters. The far point is the furthest distance at which an object can be seen clearly, and normal is infinity. If you can look out at the mountains that are far away and they look all sharp and clear, good for you. Some people can't, okay? Now, if you're nearsighted, you can see up close, some people even closer than 25 centimeters, but you can't see the mountains. And farsightedness, that's like me, I can see those mountains beautiful, they're gorgeous. But put a piece of paper in front of me and I can't read it, okay? My near point is too far away. More than 25 centimeters, okay? Now, how do we fix that? Well, let's talk about nearsightedness. What's happening there is that the light that comes from the mountains that's coming in parallel, it doesn't get focused where it needs to be focused. It's supposed to be focused nice and sharp back on the retina where the brain's ready to interpret it. But it happens sooner. And that can either happen because this lens is too weak or because your eyeball's too long. Either one of those is going to cause this problem. And so we want that convergence to happen later. And so what we do is we put in a lens that spreads the rays, okay, has negative power. And that's going to move that convergence back a ways. Does that make sense? Okay. On the other hand, farsighted like me, an object that's close gets focused behind the retina. And so where I'm interpreting what I'm seeing, it's all fuzzy because it's coming in at different places on the retina. And so what I want to do is focus these rays even stronger. I want to get more converging power. And so I put a positive lens in front here. Okay, now I've got a got a little projector here. And okay, if I take my glasses, you see how they focus it down to a smaller area than the shadow of the glasses. That's a positive lens. That's a positive. Is anyone nearsighted? Anyone have glasses that are okay? Thank you. If I put them in front of here, look at where the light is. You see that area where the light is kind of diffuse? That is spreading out the light from the projector into a bigger area than the lens itself. That's a negative lens, and your prescription is probably a negative something diopters. Okay, mine's a positive 3. Okay, so now let's sort some examples here. Farsighted eye. Sue is farsighted with a near point of 100 centimeters. Reading glasses must have what lens power so that she can read a newspaper at a distance of 25 centimeters, assuming the lens is very close to the eye. Okay, so what we want to do, Sue's eye can focus a curvature of -1 diopter. In other words, if light is coming from 1 meter from her eye, she can focus on it. That's fine. That's her near point. Okay. But not something that has a curvature of -4 diopters coming from 25 centimeters. We need a lens that will take a -4 and turn it into a -1. Okay. In other words, Um. I would like, when I put a piece of paper 25 centimeters away from Sue's eye, I would like for it to create an image, it's gonna be a virtual image, that looks like it's coming from a meter away. And so I'm going to need a power there, a positive power of 3 diopters in order to change that. Okay? So what hits the lens is gonna be the -4 because it's coming from close. And what leaves the lens to the eye, I wanna be -1 so that it looks like it's way back there. Okay? We good? Okay, let's take another example, the nearsighted eye. The nearsighted eye is a little bit easier and yet a little bit harder. There's some parts that are easier, some parts that are harder. In this case, we've got a nearsighted eye that has a far point of 12 centimeters. It's supposed to be infinity. Nowhere close. 12 centimeters, okay? And so the question is, what power is needed for this person to see distant objects clearly? Well, oh, that's a typo. The far point is 17 centimeters. My bad, okay? My bad. That's a typo. I will fix it. So 17 centimeters. But 2 of those centimeters are the distance from the glasses to the eye. And so when it gets to the glasses, the radius of curvature is only going to be the 15 centimeters. And so we would like the final curvature to be -1 over 0.15 meters or -6.7 diopters. Now, we would like for light coming from infinitely far away to come to the eye with that kind of curvature, because that's what the eye can handle. And so the initial curvature, what's coming in is from infinity, so that would be 0 curvature. And what kind of power do I want on my glasses to give me -6.7? Well, that's just -6.7. And that's a pretty strong prescription, okay? Okay. Let's quickly talk about angular size. We notice that the moon is a whole lot smaller than the sun. And yet we say that when we look up into the sky, they're roughly the same size. Well, what do we mean by that? Well, the sun's diameter is 1.4 times 10 to the 9 meters. The sun's distance is 1.5 times 10 to the 11 meters. The moon's diameter, well, those are numbers that we don't really care deeply about. What we care about is this angle between one side of the moon and the other side of the moon, or one side of the sun and the other side of the sun. And we know that the tangent of this angle is going to be the distance across, that's going to be this diameter, divided by this distance to the eye. So if I take that number and divide by that number, I get this angle that the sun subtends in the sky for us. And then if I take this number and divide by that number, I get the angle that the moon subtends in the sky. And what I get is that the angular size of the sun is just a tiny bit, 1/100th of a degree, larger than the moon's angular size. And that's why you can have an eclipse. Okay? Questions on that? Now, when you're trying to magnify something, what you're trying to do is increase that, that angular distance, that angular, spread there. And the easiest way to do that is with a magnifying glass, which is just a converging lens of positive power. And if I put that magnifying, if I put the object right inside the focal length, I'm going to get a virtual image that is much, much bigger than the real thing. And so the angle that it's going to subtend is going to be much bigger than if I didn't have the lens. Okay, now, how much magnification do I get? Well, that's going to be the ratio of this angle here to this angle there. And what I find, we're not going to go through the derivation because we've got 3 minutes, is that there's 2 ways that I can look through a magnifying glass. I can look with a relaxed eye where I'm not straining. And when you're looking at the mountains, your eye's relaxed. It's not pulling on those muscles. You can do that while you're sleeping, okay? And if you have your eyes relaxed, where the near point is near, N is the near point distance, and so this is with your eye focused at infinity. And your near point is 25 centimeters. What we get is the near point divided by the focal length of the lens. Now, if instead you're focusing on something at the near point, then you get an extra 1 in the magnification. It's what you had with a relaxed eye plus 1. So if I look at this example here, where I've got an 8 centimeter focal length converging lens, with a relaxed eye, I get a magnification of 3. If I focus at the near point, I get a magnification of 4. I think we've had enough for the day, right? Our brains are full. Okay.
Why not?